All right, guys, so today we're going to talk about Kepler's three laws. So Kepler was a man who lived from 1571 to 1630. He improved upon Nicholas Copernicus's heliocentric theory. He fit Tycho Brahe's observational data into mathematical models, and this is what his math and his foundations are actually what inspired Newton's theory of universal gravitation. So we're going to spend the rest of this 9 weeks, which isn't long, talking about Kepler and his three laws and what they mean for us. So the first thing Kepler said is that every planet's orbit is an ellipses. Ellipses. And the sun is at one of the focus points. So an ellipses has to have two focus points. So we're going to go up here. And if these two focus points are really close together, their orbit is going to be more circular or nearly circular. And if the ellipses or these two focal points are farther apart, that ellipses is going to make an oval shape. So if they're far apart, we get this oval shape. And it's an elongated ellipses. And this is the shape that comets make. So this is how comets get their shape. The longest period for a comet in this oval ellipses shape is over 200 years. Or sorry, for a long period comet, that's a comet that only passes into our view or passes us. All right. Sorry, I've regrouped my thoughts. A long period comet is a comet that takes more than 200 years to pass by the Earth. The longest comet we have, just as a fun fact, is called the McNaught comet. And that comet passes by in our view, or passes by that focal point, once every 93,000 years. So that's a really, 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 really long time for an orbit. Our orbit is 1 year. Imagine 93,000 Earth years for one orbit. A short period comet takes less than 200 years to complete its orbit. The most popular example of a short period comet would be Halley's Comet. If you watch Big Bang Theory, that's what their daughter Halley is named after. And its period is 76 years. That's why they typically say in your lifetime you only get one chance to see Halley's Comet in real life, because a typical human's lifespan is around 80 years. So that comet will only pass by the planet Earth once in your entire lifespan. So if you are alive and able to see it, it is something to see. It's kind of like a shooting star is what it looks like almost. The next thing we have, or the next point that Kepler made, was that the line that joins the sun and the planet sweeps out equal areas. So basically all that's saying is that this area is equal to this area. That's all that says. So if that line that joins the sun and the planet sweeps out equal areas in equal amounts of time. So if T1, so change in time 1 is equal to change in time 2, then A1 is equal to A2. So this right here is change in time 1. And this right here is change in time 2. So that's saying that it has equal areas and equal amounts of time. So if it takes them 2 hours to go from here to here, then it takes 2 hours to go from here to here. And that those areas are equal. This refers to each planet, moon individually. So it's not between the sun, the Earth, and Mars. It would be between the sun and Mars, or the sun and Venus, or the sun and Pluto. Oh, Pluto's not a planet anymore, I guess. The sun and Neptune. So it's each planet individually, and each moon individually has its own. The last one of Kepler's laws is the square of the orbital period is proportional to the cube of the orbital radius. So let me write that out for you. The square of the orbital period is proportional to the cube of the orbital radius. So the period is how long it takes to get around one time. The radius is the length from the center to that planet. We call this Kepler's constant. So that's what that K stands for. That K stands for Kepler's constant. And it's measured in seconds squared per meters cubed. This T2 stands for our orbital period. How long does it take to get around one time? And if we're measuring how long, we're going to measure that in seconds. Radius is how far, or our orbital radius is what that R stands for. And if we're measuring how far, we're going to measure that in meters. Kepler's law doesn't only hold true for the sun and the planets. Kepler's in the planets in Earth's solar system. Kepler's law holds true for any motion of two objects around a single body. So hopefully at some point in your life hopefully this is not going to be the first time you hear this is when I talk about it right now, someone has explained to you that the Earth doesn't revolve around the sun. The sun and the Earth are both revolving around each other. And there's two different points that they're revolving around. We talked about them up here with the focal points, but they're not exactly center. And that's why some of them have a more elliptically shaped orbit than others. So the Earth's orbit is it is elliptical. We like to draw it as a perfect circle, but if you look on your paper, it's not a perfect circle if you were to measure it out. So its orbit is elliptical, but nearly circular. And that's because both of the focal points are in the sun. All right, so those are Kepler's 3 laws. Those are what he said. They're his 3 laws of planetary motion, and they hold true for any planet in any solar system, in our galaxy or any galaxy that we might discover outside of ours.